So we've got a tilted axis problem, which is a common motif in this unit of the class. It sort of ties together a lot of ideas. You really have to understand force diagrams and how to manipulate them and how to think about the different equations, as well as testing your knowledge of geometry all in one problem. So this is a common problem to deal with. So let's get to reading here. An 8-kilogram block is hanging from a rope and an angled surface as shown in the figure. A. Draw a force diagram of the block and identify all types of forces. B. Find all the forces in vector component form, I hat and j hat, with respect to the tilted axis. The picture shows a square block resting on an angled surface and held up by a rope. And so this could be a mix of friction in a different problem or other forces. And then also think about what happens if you, say, cut the wire and the block started falling or accelerating down the ramp. This is where tilted axis comes into play. When you tilt your axes, it is aligning with where the direction of motion would be, or direction of acceleration would be, and it actually makes the problem easier. It looks like it makes the problem more complicated, but it will make the problem easier, but it's a new type of thing that you have to tangle with. In our problem, it's not accelerating, it's staying in one spot, and so this is a statics problem. It's static, not dynamic. Now, when it comes to tackling forces, we can follow the book's advice and look at trying to identify them by drawing the picture and following a few steps. So we're going to draw the picture and then encircle it with this. A red circle is what they've got. Let me get my pointer out here, as they've got right here. And whenever you see that this circle intersects with something, so if you look at this picture, it intersects with this rope, that's where you have to stop and think and say, look, there's probably a force involved in this interaction where there's touching. Now, you want to label each of these, as here they've had it labeled as tension. And then finally, you want to identify any long-range forces, and the only ones that we're really going to think about are gravity and possibly the electric force, but if not, we'll save that for a different class. So really, it's mostly just gravity. Is this person here supposed to be experiencing gravity? Yes. Okay, then let's make sure we put that into our system. This is already drawn for us. We don't have to do that step. And so let's go ahead and draw the circle as they have recommended. We are interested in the block. So if we encircle this block, we might have a little circle like this. And we see that there are a few contact points, right? Let me put these in purple. There's one right here with the rope. And well, it's resting on this surface. So this whole part here also has some sort of a contact and so a force that we may need to consider. Okay. If we also want to consider, well, is this supposed to be experiencing gravity? Well, we're assuming it's on Earth, so yes, it also has this long-range gravitational force. And if we want to identify them, right, so this one is gravity, it's kind of like given, almost always going to be a part of our system. The top one, when we meet a rope or a wire and we're pulling on that wire, that is called tension. Okay, and then we have this surface where it's interacting with the surface. There's a few ways to interact with surface, and they are friction, which is where you are sliding. So if there's a surface and you are sliding up or down, or we're preventing any sort of sliding, that would be the case here. However, we want to always assume that there is no friction unless otherwise stated, okay? And so here, we said nothing about friction. So we do the classic physicist thing and pretend that everything is made out of ice and friction doesn't exist. There's another surface force. When there's a surface, right? Well, actually, let's do a simple sort of flat horizontal surface. If you put something on a surface, gravity wants to pull it down, but it is prevented from going down because there is a normal force pushing up, and that does not need to be on a horizontal surface, and so there is an out of plane normal force. Normal here refers to the mathematical sense of normal, not like typical. Normal means orthogonal, perpendicular, or away from a surface is what normal means in math. And so our forces here that we have are the normal force, we have tension, and we have gravity. And I didn't see any other intersections with this red line, and so we can be fairly confident that there are no other forces at play. And again, you could argue that friction could play a role, but not if we didn't say so. Okay, so let's go ahead and do part A, draw a force diagram of the block. Now, you could draw the block here, but we can just represent it by a point at the center of mass of the block. So tension, it's already got this direction sort of built into the wire. If you think about what direction is tension pulling on the block, it's going to be, well, exactly where the line of the wire is. And so that's going to be sort of in this direction. We're sketching. We don't need to be exact. Gravity always goes down, and so that's this way. It always goes towards the Earth. The normal force is always away from the surface, and so that direction will be like this. Gravity is down, but our axes are tilted, and so we do have to be careful here. Our x, we're going to say, is going to be this way, and y is that way. Not, as you may typically see, right, as we've seen for most of the problems, x is this way, and y is this way. X is to the right, and y is up. We're not going to do that in this problem, and that makes it perhaps a little bit more challenging. But that does mean that gravity is not pointing in the negative j hat direction as it normally is. Okay, so how are we going to proceed here and actually find these in vector component form with I hats and j hats? So I did give you this hint that I hat usually means right and j hat usually means up, but we are redefining those directions a little bit, okay? We are going to want our answers to look something like, the force of gravity is equal to something something I hat plus or minus, something something j hat. And these I hats and j hat don't refer to right or left. They refer to sort of this parallel to the surface here or perpendicular to that surface. And so that's what we're going to want as our answer at the end of the day. Something I hat, something j hat for each of these forces. So the key here is that this is a static problem, and that means that the forces are balanced. And so if I quickly redraw our force diagram, so this was tension, Ft, this was the normal force, Fn, and by the way, we sometimes use, just whatever you prefer, just T for tension with a little vector form, or just a lowercase n for the normal force. And Fg, gravity. Now, the key here is the forces are balanced, and so all of the x and y components of this system, if you were to add them all together, must total 0. And before we get there, let's first talk about how do we solve for these values. Well, the tension force, what equation do we use? There is none. There's not an equation for tension. Tension is sort of reactive to the rest of the system. And what about the normal force? Same thing. There's not an equation for the normal force. So we don't really have a way to say, oh, Fn equals blah, blah, blah. It's not always that simple. There's not a formula that always applies. However, for gravity, there is a formula. There's a complicated version for when you're in outer space, or there's an easier version that it is m times g downwards is the gravitational force. And in this case, we have these values. We have the mass, which is 8 kilograms, and we have g, which is 9.81 meters per second squared. And so the vector is 78.48 newtons downwards. The magnitude, right, is 78.48, and the direction is downwards, but downwards is not along our x or y directions, and that can be a little bit tricky. What we're going to do is split the vector into its x and y components, right? So the x component is going to be this part of the vector along the tilted x-axis. You can call this fgx, and the y component is along this part, and this is fgy. And to find these values, we're going to need a little bit of trig and a little bit of geometry as well. So looking at the picture real quick, so gravity is down this way, right? Using a parallel lines theorem, you can see that this 17 degrees is actually going to be equal to this 17 degrees as well. And we're going to use that back up on our force diagram. We'll put that 17 degrees up here. We're going to use that in order to form a right triangle, and then we can SOHCAHTOA, we can Pythag, we can get all the values that we need. Do be careful. Oftentimes you're not given the 17 degrees. It's more natural to only give you the angle with respect to the floor, which is 73 degrees, in which case you would not be given this angle. You'd be given the other angle on the other side of the triangle. So you would need to say subtract 90 degrees, or just be careful about which of SOHCAHTOA you're using. Let me redraw that, just that triangle. FGX is right here, FGY, and FG I had drawn in blue. And now we ask, I don't know what FGX is, but I do know what the total FG is. This is what we had computed right here. This was the 78 newtons. That looks like a hypotenuse to me. I have 17 degrees, and I'm looking for FGX. So how do I combine these? FGX is adjacent to the 17 degrees, and so that sounds like a cosine. But we do want to be very mindful of our axes, right? If this is x and this is y, our FGX is pointing opposite to the x direction, and so it has to be a negative value. The raw trigonometry here, opposites and hypotenuse is cosine, so cosine theta is adjacent over hypotenuse. I do know the angle. The angle is 17 degrees. The adjacent is the unknown FGX, and the hypotenuse is known. That's the 78.48 newtons. We do want this guy, we want him to be negative because he's going to be pointing opposite. If that bothers you that we're just placing a negative sign in there, then you may want to start this problem from the positive x-axis, looking at the force diagram here, and going like this, going all the way around, and you want to do the cosine of 197 degrees. That will give you the negative sign. I think that's a little bit finicky. It's easier to just understand that FGX has to be negative. Whatever it comes out to be, it must be negative. And so we could just slap in that negative sign. And then you can do this, and you will get that FGX, do a little bit of algebra, is equal to negative 75.05 newtons. Okay, we're making some serious progress now. We have the x component of FG here. If you got 21.6 newtons, that means that your calculator is in radians, and you want to double check that. Make sure that it's in degrees if I gave you 17 degrees and not 17 radians. We can do the same thing for FGY. I'll just skip to the same idea that FGY is going to be equal to, well, it's going to be equal to negative 78.48 newtons sine of 17 degrees. Should be negative 22.95 newtons. Once again, we put in the negative sign because it is pointing downwards. How do we find Ft and Fn from this information? We use the fact that this is a static problem and Newton's second law applies, that net force F net is going to be equal to mass times acceleration, but in this case it's static, so that's 0. That means all the x components and all the y components will balance. This is where finally it is easier to have used a tilted axis because tension is purely in the x direction and the normal force is purely in the y direction. And so they will balance the x and y directions of gravity respectively. And so our final answer, right, is that tension is equal to, as a vector, well, it has to balance gravity, so it's 75 newtons I hat. The normal force is equal to, actually let's call it 23, let's go ahead and round 23 newtons J hat. Fg is equal to negative 75 newtons I hat minus 23 newtons J hat. It's a long problem, and again, it tests geometry, trig, and your ability to draw a force diagram. And so I think it's a multi-level problem, and it's a good one. Hopefully that made sense. If not, you can always ask questions in class or in the comments. Maybe I'll see it. But yeah, see you in the next one.